thermal expansion. So let's take some, we know that even liquid, solid, gases, any object will expand. So let's take some. So I'll start with the say simple solid because you are very well aware of this. So this is at temperature T1 degree Celsius and it's having a length L1. I will write the temperature. Okay, let it be capital letter. Then at higher temperature, this will become length L2. See, what is the in general property? So to construct, shall I use this idea to construct a thermometer? And we know that what is the change in length? This change in length is it directly proportional to the temperature? Yes, it is. Delta L is equal to L1 alpha delta theta. Look at this delta L, directly proportional. See, I would have thought first thermometer. It's a wrong thing because you must know expansion first. Once you know expansion, then you can enter into thermometry. That's why I didn't start with thermometry. Okay, no, so the here, so what is the property like? So we are going to take help of a property of a substance. What happened where its dimensions are going to change as we rise the temperature. Example, I took the rod, or you can do one thing. So like I will take liquid, even the liquid also. Suppose there's a liquid is there. Okay, it's having some volume V1 at T1 degree Celsius. Then I'll rise the temperature. Then the new volume will become V2 at T2 degrees Celsius. So shall we express that change in temperature in terms of change in volume of liquid or change in length of solid or gases? Because when you supply heat, so we know that it's having a pressure P1, volume V1, temperature T1 degrees Celsius, T1, let's assume that one. I will supply heat. Then because of that, let volume be constant. And I'll bring like this. If volume constant, volume, let it be that one. So this will become P2 V T2. Just logical thinking, nothing big. So here there's a gas. So what parameter of gas has come constant? Volume of gas constant. Even I can take help of amount of gas, which is having initial pressure P1 and temperature at temperature T1. When I supply heat to it, the pressure will become P2 and temperature T2. So can I express now this change in temperature in terms of change in pressure? So can I use to measure temperature by measuring the change in pressure? For a liquid, if I supply heat, there's a liquid. So when I supply heat, so on its own temperature will not increase. So we have to supply some certain amount of heat. Then the liquid will expand, the liquid will absorb that heat and will expand. So temperature, the volume of the liquid has increased. So therefore, can I express now this change in temperature in terms of change in volume? Yes, it is. So this is the property of a material. Like a liquids, what I can measure very easily, change in volume. For a solids, the change in length or change in area, these things I can measure. Now the gases, one more advantage with the gases is, instead of this, it can also happen that this is the pressure will be constant, whereas the volume of gas will be changing. Okay, I think I'll give better diagram. These are some ideas I'm trying to give. So this is having initially, say, atmospheric pressure, air is there. So what are the forces that are acting? P naught A, mg, Pa, similar to liquid here. So this gas is present. I think I'll draw a big diagram. This you find very difficult. Okay, look at this one. Now next property of gas, what I'm going to do is, this is air. So what are the forces? Mg, P naught A, pressure of a gas PA. There's a volume V1 at temperature T1. Now I'll supply heat to this. So then what will happen is same volume. No, you see this. So what is this? This one is, it's a piston of what is the volume V2, temperature T2. Now what quantity? The pressure of gas is constant. No, I think you know enough of some fluid statics idea. There's a gas. So what is P equal to? P naught plus mga. Now look at this. What has changed here now? Volume of gas change. No. So can I now construct this property? Shall I use what property? Like the change in volume of gas also can be used to measure the change in temperature. Able to see this? I'm giving rough diagrams, so you can really think on it. Rest of everything formula, and this chapter, this topic will get over, and some theoretical information given, advantages, disadvantages. So I think just if you want to read once, may not be very important, I feel, and different types of scales. There's a gas. Volume is constant. Volume will not change. So I do have all this I'm putting. So now you can ask questions, sir. What is use of that solid one? How you can measure? So we know this is the, so we'll, area of cross section is A. Now also it is A. And what is the resistance of this? Resistance into rho. Rho is not this one. It is a resistivity into L1 by A. Rho L2 by A. What is rho here? Resistivity of material. For different materials, it will be different. Have this much here. So now I do have different methodology. What is that? By changing length of a solid, I can measure the change in temperature. This is nothing but resistance thermometers. In liquid thermometers, by as the liquid absorbs heat, the liquid will expand. So the change in volume of liquid I can use to construct liquid thermometers. Gas thermometers, there are two methods are there. Either I can keep pressure of gas constant or volume of gas constant. I'll supply it. Here, I'll fill up this gas in a fixed container, rigid container. So volume of gas is constant. So as temperature changes, pressure will change. So the change in pressure will help us to find out what is the change in temperature. So this will become constant volume gas thermometer. Now here I'll supply heat. So what happened here? The gas will expand, but the pressure of gas remains constant. You can see P naught will not change. Why atmospheric pressure will change? Should not change, no? Why atmospheric pressure will change? The weight, this will also not change. So therefore pressure of gas is constant. So this will become constant pressure, constant volume, constant pressure gas thermometers. These are the methods what we'll be using. Let me put it here. This is the idea for liquid thermometers. Okay, this one. So this is the constant volume gas thermometers. Just simple ideas, nothing big, no? So a small basic observation you have to make it. So this will be constant thermometers. So let me segregate all. And or this will be resistance thermometers. I think this will be much easy for students to really understand. Okay, what is a thermometer now? It's a device which is used to measure the temperature. Fine. So what is the, agreed all of you? So this is the idea is what I generated. Okay, now let's get into the different types of the thermometers which we are going to learn it and we'll write the formula. So now altogether, you see that one. So rather than you see that here length I'm taking, here what happened, the volume of liquid, here the pressure of gas, here the volume of gas. Means some means like a some property of a matter, like all these what their property, no? So whenever a matter, whenever a substance absorbs heat, there'll be some changes will be noticed in a substance. So that particular change what happen if I'm able to express it in terms of change in temperature, nothing but that device now will work as a thermometer. Are you getting the methodology? Able to understand? So the change in property of a material due to change in temperature of a material, what happen is what is used to construct the thermometers. Able to get this? So that change in property is a general thing. It can be any of the quantity. It need not be always this one. It can be any of the quantity, you know. Okay, now let me write some few definitions which are there. Thermometric property. What it is, no? It is the property used to measure the temperature change in any quantity it is used to measure the temperature changes any quantity that changes which change in temperature, and that can be used to measure temperature. Okay, there's some, what is the meaning of this? So here I took a rod, some wire, I will raise the temperature. The length is varying. The length is varying with the temperature. So therefore, the change in length is what I can use to express change in temperature, and that is what I'll use to measure the temperature. Here, change in volume of liquid. Here, change in pressure of gas. Change in volume of gas. So what is the? This is a property of a substance. So now you cannot ask here, so like I want to measure change in pressure. No. So what? As you vary the temperature of substance, what parameter you can measure there very easily, what change in parameter you can measure very easily, that should be utilized to measure change in temperature. Are you getting this one, sir? Here I'll measure the change in pressure. Not possible. My pressure will change here. Getting the idea? So that's what I mean to say thermometric property here. So in the first diagram, what is the thermometric property? Change in length. Second diagram, what is the thermometric property? Change in volume. Third diagram, what is thermometric property? Change in pressure. Fourth diagram, what is the change in thermometric property? Like a, it's a like a volume of a gas. So I'll write it here. So what is the thermometric property here? Here is change in length. Thermometric property. I'll write TP here. TP here is change in volume. So what about here TP? TP here is change in pressure. What about TP here? Okay, fine. Some rough idea like this we are considering. Okay, let's go for. So this is so that the property is something. It can be anything. No? So the thermometric property can be anything. So how to generalize it? So we need a general method. So therefore, I'll begin like this. Let's. So the thermometric property at any temperature, let it be the thermometer property be have a parameter xt, then alpha t. Then at 100 degrees Celsius, let it have a parameter x100, 1 plus 100 alpha. Okay, this can be further written as xt minus x naught equal to x naught alpha t. This will be x100 minus x naught equal to x naught 100 alpha. Let me divide these two. X naught get cancels, alpha get cancels, t by 100. So therefore this t is what now? Now what is this? So we are going to put it like a, what is x naught? X naught is the lowest one. So here, so this is the x naught at 0 degrees Celsius, at 0. We take that 0 as reference, no? So then this is x100 at 100 degrees Celsius it is. Then xt, so it will be t degrees Celsius. So what is x? X can be anything. It can be length. It can be volume of a liquid. It can be pressure of a gas. It can be volume of a gas. So it's not a rod. It's not a rod. I'm just drawing a scale like that. So this, I think, generalized formula which we have just introduced here. So shall we say this is the upper point? Shall we take this as upper point? Okay, fine. So this is a upper point and a lower point, UP, LP, like this. Some books they're given symbol. If you want, you can use lower reference point, upper reference point, any of the symbols, which all you feel convenient, you can use them. Now, from where this equation I brought it? Just now we had a, so shall we call this as the ice point? Steam point. Anything, no? So the 0 degrees is what you can, where the ice will, water will freeze, water will get freeze to ice and ice will start melting. So therefore I'll call that as ice point, steam point, where the water what happen at 100 degrees will become steam at 100 degrees. So therefore I'll call this 100 degrees as steam point, ice as this point. So these are the things reference. There's a lower reference point, which I'm going to take that one because I need reference, no? So what is the reference? I'll usually go for the highest point as reference here. because I should say temperature at a 30 degrees with respect to what 30, with respect to 0 degrees, it is 30. So therefore lower reference point is needed, upper reference point is needed. Upper reference point, steam point, it can be because we can have a